Wyoming is moving. Right now, as you watch this, the ground beneath one of America's most visited landscapes is rising, pushed upward by a magma plume so vast that geologists classify it as one of the most dangerous volcanic systems on Earth. But here's what's strange. Most people think of Wyoming as empty, a flat, forgettable flyover state. And statistically, they're not wrong. It's the least populated state in the entire country. 590,000 people in a land bigger than the UK. What if I told you that emptiness isn't an accident? That the geology of Wyoming is directly responsible for why almost no one lives there? And why, if a single geological process shifted even slightly, it could affect millions of people across the entire American West? This is Wyoming, and it is far stranger than you think. To understand Wyoming, you have to go back roughly 70 million years to an event geologists call the Laramide Orogeny. Most mountain building events work like this. One tectonic plate dives steeply under another, generating heat and pressure close to the surface. Mountains rise near the coast. Neat. Predictable. But something went wrong, or rather, something went unusual, with the Farallon plate. Instead of diving steeply into the mantle, it subducted at an almost flat angle, sliding beneath the continent like a piece of paper under a table. The pressure didn't release at the coast. It traveled inland, over 1,000 miles inland, and it crumpled the crust of what is now Wyoming like a slow-motion collision. The result? Wyoming's ranges don't follow the typical north-south pattern of the Rockies. They punch up from the plains at odd angles. The Wind River Range, the Bighorns, the Laramie Range, each one a consequence of that ancient, shallow slab of ocean floor that no longer even exists. The Wind River Range is one of the most dramatic consequences of this process. The range contains 63 named glaciers. These glaciers cover approximately 17 square miles and include 7 of the 10 largest glaciers in the lower 48 states. Some estimates indicate up to 679 total perennial ice and snow bodies, of which a smaller portion are classified as active glaciers. The largest is the Gannett Glacier, which is also the largest in the U.S. Rocky Mountains. The glaciers shape the land, exposing the mountain's core, ancient Precambrian granite, over 2.7 billion years old. To put that in perspective, those rocks formed before complex life existed on Earth. They predate the dinosaurs by over 2 billion years. And then there's Devil's Tower. From a distance, it looks like something that shouldn't be there. A hexagonal column of rock, 1,267 feet tall, rising abruptly from rolling plains. It was the first U.S. national monument, declared in 1906. But what is it? Devil's Tower is a phonolite porphyry. Phonolite is an alkali-rich, silica-poor volcanic rock, while porphyry signifies it has a mixed texture of large crystals, phenocrysts, embedded in a finer-grained matrix, indicating a two-stage cooling history. So how did that happen? The magma that produced Devil's Tower intruded into surrounding sedimentary rock layers and cooled slowly beneath the surface, forming the distinct hexagonal columns through contraction as it cooled. Its formation is actually still debated. Was it a laccolith, magma that never broke the surface, a volcanic neck? The geology is genuinely contested, and that uncertainty is part of what makes Wyoming so interesting. Even the landmarks we think we understand still hold open questions. Most mountain ranges announce themselves gradually. You drive toward them, the hills grow, the elevation climbs, and eventually, mountains. The Grand Tetons don't do that. They erupt vertically. From a flat valley floor called Jackson Hole, the peaks rise more than 7,000 feet above the valley floor. There are no foothills, no warm-up, just the sharpest, most abrupt mountain front in the entire Rocky Mountain system. That abruptness is the point, and it's geological. The Tetons are what's called a fault block range, formed not by two plates colliding, but by the Earth's crust being pulled apart. The Teton Fault runs along the eastern base of the range, and over roughly 6 to 9 million years, the western block, the mountains, has been thrust upward, while the eastern block, Jackson Hole, has dropped downward. The total displacement across that fault is estimated at over 30,000 feet. While the mountains look massive, the actual vertical throw, the total distance the two blocks of crust have moved past each other, is nearly double what we see with the naked eye. To visualize the sheer scale of this movement, we have to look at the Teton Fault. This is a 40-mile-long crack in the Earth's crust, where the mountain block, the Horst, moved up, and the valley block, the Graben, dropped down. During the Pinedale glaciation, 32,000 to 12,000 years ago, it formed massive ice caps, up to 4,000 feet thick. Glaciers carved the sharp, jagged peaks, U-shaped valleys, and created lakes like Jenny and Jackson by leaving behind moraines. What makes this especially striking geologically is the age of the rock being exposed. The glaciers that carved the Tetons' iconic sharp arates and cathedral peaks during the last ice age were stripping away sedimentary cover and revealing Precambrian basement rock, gneisses and schists over 2.7 billion years old. Continental collisions created gneisses, followed by magma intrusion that formed the granite. The same ancient crust we saw in the Wind River Range. Wyoming keeps returning to this theme. Ancient rock, violently re-exposed. The Teton Range remains one of the most active fault systems in the Rocky Mountains. Jenny Lake sits at the base of the range, occupying a basin carved by a glacier that flowed out of Cascade Canyon during the last glacial maximum. The moraine, the debris ridge the glacier left behind, dammed the valley and created the lake. It's a simple story once you know it, but standing at the shore, the scale of what moved through here is hard to process. Jackson Hole, the valley cradled by the fault, tells a human story that mirrors the geological one. Settlers who arrived in the late 19th century found an isolated basin, hemmed in by mountains, with a short growing season and brutal winters. The Monroe homesteads, now a historic district within Grand Teton National Park, are among the most photographed structures in America, precisely because the backdrop makes everything feel monumental. The settlers weren't surrounded by mountains. They were surrounded by the exposed edge of a geological rupture, 9 million years in the making. The Tetons are young by geological standards, younger than the Appalachians by hundreds of millions of years, younger even than the ranges built by the Laramide Orogeny. And because they're young, they haven't had time to erode into soft, rounded shapes. They're still raw, still sharp. A fault that hasn't finished moving, the Teton Fault, remains seismically active, producing a mountain range that looks like geology happening in fast forward. Beneath Wyoming's northern plateau lies something that geologists treat with a particular kind of respect: the Yellowstone hotspot. A hotspot is a column of superheated material rising from deep within the mantle, largely stationary while the tectonic plate above it moves. The North American plate has been drifting southwest at about 2.35 centimeters per year, causing the hotspot's active center to migrate northeast over time. Over this hotspot, for roughly 16 million years. The result is a chain of ancient calderas, collapsed supervolcanoes stretching across Idaho like footprints of geological violence, heading northeast toward where the hotspot sits today, Yellowstone. Research from the University of Utah has imaged a dual-chamber system, a shallow rhyolite magma chamber, 3 to 9 miles deep, and a much larger, deeper basaltic reservoir, 12 to 28 miles deep. The Yellowstone Caldera is approximately 34 by 45 miles across. It last erupted in a full caldera-forming event 640,000 years ago, releasing roughly 240 cubic miles of material. But here's the thing about Yellowstone that's easy to misrepresent. It is not overdue for an eruption. The notion of a predictable eruption cycle, that it blows every 600,000 years, therefore it's due, is not how volcanology works. The intervals between past eruptions were 2.1 million, then 1.3 million, then 640,000 years. There's no clock. What is true is that the system remains intensely active, and monitoring it gives scientists a window into processes happening miles below the surface in real time. Current imaging shows that Yellowstone's shallow magma reservoir is only about 5 to 15% molten. To trigger a major eruption, scientists estimate that at least 50% of the chamber would need to be liquid magma. Yellowstone hosts over 10,000 geothermal features, 500 of those being geysers. Grand Prismatic Spring is the largest hot spring in the United States. Its colors aren't pigment, they're microbial life. Heat-loving bacteria called thermophiles colonize the cooling margins of the spring, and different species thrive at different temperatures. The deep blue center is too hot for anything to live. The orange and red margins, that's billions of organisms doing what life has done for 3.5 billion years, adapting. Old Faithful erupts roughly every 90 minutes, but that regularity is a quirk of its specific plumbing, not a feature of geysers generally. The timing of each eruption predicts the next one. A longer eruption means a longer interval before the next. It's a pressure system, a simple, readable signal from an impossibly complex underground world. The Grand Canyon of Yellowstone adds another dimension. The canyon's vivid yellow coloration, which gave the region, and eventually the state its name from the Minotari tribe's phrase meaning Yellow Rock River, is the result of hydrothermal alteration. Hot acidic fluids have been chemically transforming the rhyolite rock for hundreds of thousands of years, breaking down iron-bearing minerals into the yellows, reds, and oranges visible today. The lower falls drop 308 feet, more than twice the height of Niagara Falls. The water volume is lower, but the drop is dramatic, and it marks the point where the river enters the canyon that the hydrothermal system spent millennia weakening, allowing the river to carve far deeper than it otherwise could have. Yellowstone doesn't just shape rock, it shapes ecosystems. The geothermal heat keeps parts of the landscape snow-free in winter, concentrating wildlife in specific corridors. Bison, elk, wolves, their movements are partly dictated by a volcanic system they have no awareness of. The geography is the biology here. Look at the United States from space at night. The coasts are on fire with light. Even the Midwest glows. But there is a region in the interior, anchored by Wyoming, that is closer to darkness than anywhere else in the lower 48. Wyoming has roughly 5.96 people per square mile. For context, New Jersey has over 460. Even Alaska, despite being vastly larger and far more remote, has similar population density. So why? Why, in a country of 330 million people, has this particular landscape remained so empty? The answer starts with elevation and geography. Wyoming's average elevation is the second highest of any U.S. state, about 6,700 feet above sea level. Much of the state sits on the Wyoming Basin, a high-altitude steppe caught between mountain ranges. The Rockies to the west strip moisture from Pacific air masses. The result is a cold, semi-arid interior that averages very little precipitation. Agriculture at scale is difficult. The growing season is short. The wind is relentless. Wyoming is consistently one of the windiest states in the country. Early settlers who attempted farming on the high plains frequently failed. The land simply doesn't yield easily. Water is scarce and critical. The major rivers that originate here, the Green River, the Snake, the Yellowstone, flow outward to other states. Wyoming is a water source state, not a water user state in the conventional sense. The Colorado River Compact, negotiated in 1922, allocated Wyoming water rights that ranchers and municipalities still depend on a century later. The Kilpecker sand dunes in the southwest illustrate how extreme this landscape becomes. One of the largest active dune fields in the world, in Wyoming. Not the Sahara, not the Arabian Peninsula, Wyoming. It's a reminder that the basin's climate is genuinely desert in character, kept cooler by elevation, but not by moisture. Wyoming is not empty because people haven't tried. It's empty because the geology made it that way. Ancient mountains blocking rain, a volcanic plateau lifting the land above comfortable living, a high-altitude basin that rewards only the most adapted life, human or otherwise. The same forces that make it hostile make it extraordinary. The same supervolcano that could, in theory, reshape the continent is the reason the most vivid colors in nature exist right here. The same ancient tectonic collision that raised the Wind River Range preserved the oldest exposed rock in North America. Wyoming doesn't fit neatly into the story Americans usually tell about their landscape. It's not the fertile Midwest. It's not the sun-baked Southwest. It's not the dramatic Pacific Coast. It occupies a category of its own, a place defined entirely by forces that preceded human beings by billions of years and will outlast us by billions more. What we've covered today isn't a collection of interesting facts. It's a single, connected story. The Laramide Orogeny crumpled the crust and built the ranges. The ranges blocked the moisture and created the semi-arid basin. The basin stayed empty, which preserved the landscape, which is why Yellowstone and the Tetons exist as we know them today. The geology explains the ecology. The ecology explains the emptiness. The emptiness explains why, when you stand almost anywhere in Wyoming, you feel something most of the modern world has lost access to: genuine scale. The Teton Fault is still slipping. Millimeters per year, imperceptible in a human lifetime, enormous over geological time. The Yellowstone hotspot is still active, still feeding heat into the system, still producing the most concentrated geothermal landscape on Earth. The Wind River glaciers are still moving, still carving, though shrinking now for reasons that have nothing to do with tectonics. Wyoming is not a finished place. No landscape is. But Wyoming makes that fact harder to ignore than almost anywhere else. The ground moves here, the water boils, the mountains are still rising, and somehow, in the least populated state in America, you can still find a patch of earth that feels like it belongs to deep time, not to us. If you made it this far, you already know this channel isn't about surface-level geography or geology. Every state, every landscape, every border has a story that goes deeper than most people realize. Sometimes, literally. If that's the kind of thing that keeps you up at night, subscribing is the most logical thing you can do. Thanks for watching.